Hi, I'm Jichen Wang from Math Program. This video introduces my thesis research, which is about the light-responsive facade system. There are mainly 4 chapters: Introduction, Simulation and Geometry, Material and Prototype, and System Design. First, let's get started with the topic Introduction. The concept of responsive architecture was first introduced by Nicolas Negroponte during the late 1960s. Precedents vary in different scales and technologies, and this thesis mainly focuses on the scale of facade. For large spaces with a long working hour requirement, such as offices and libraries, there are usually glare problems caused by large openings or glass curtain walls, but people are unable to adjust the shading elements one by one. So I want to develop this automated light-responsive facade system to improve the light condition for this kind of space. Unlike a lot of research and practical works only dealing with the openness of the facade elements, the facade system in my thesis takes the reflection attribute of the light into consideration and aims to create a good interior light condition with sufficient and uniform light distribution. To achieve the design target, I also developed an evaluation tool to simulate the light behavior and optimize the facade geometries. Now, let me introduce the evaluation tool I developed in detail and show how the design process improved along with the evaluation. In the evaluation, I suggest that enough illuminance and the uniformity of the illuminance make a good light condition, and they can be calculated in these formulas in architectural physics. This diagram shows the overall algorithm. The simulator will take the sun angle and facade geometries to calculate the fitness value, combining the illuminance and the uniformity. Then the optimizer will give feedback to the input parameters to change the geometry and optimize the fitness value. For each input geometry, there is a parameter from 0 to 1 indicating the transformation of the surface. Sun angle is a vector determined by location and time. In the simulation, each photon is treated as an agent and has its own behavior against different material. And there is a grid of cells to capture the light energy at the working level. The cell capturing more light will be mapped with warmer color. Using the genetic algorithm, the optimization will change the initial parameters of the transformation for a better fitness value. In this design space analysis, the red line indicates the illuminance and the blue line indicates the uniformity. We can tell that there is an opposite relationship between the two properties. Therefore, illuminance and uniformity are weighted and combined into a single fitness function so that we can achieve a balance between them. At first, I tested a group of simple geometries with flipping, rotation, and bending transformations. We can tell that horizontal rotation and diagonal rotation work better in balancing the light intensity and uniformity. Therefore, I developed more geometries within these two categories, such as corner flipping, interweave diagonal rotation or flipping, horizontal bending, opening rotation, and double-sided rotation. I evaluated these geometries with a unit scale and recorded their behaviors through time. The red line shows that the last type with horizontal twisted panels works better than others all the time, since it could handle a large range of sunlight angles. Along with the digital simulation, I also made prototypes to gain the idea of transformation mechanisms and material behaviors. For the material, there are 2 parts: actuator and functional panels. The actuators should take digital signals and be able to deform. The panels should be flexible, light, and reflective. I tested both shape memory alloys and motors at the actuators. The shape memory alloy can only achieve a limited range of transformation and is hard to control. Therefore, finally, I chose several motors to control the rotations of the panels for the prototype. Panel geometries are developed along with both the simulation and the prototypes. For the option that behaves best in the simulation, I designed a unit to test the real behavior with a multiple sensing system. Ideally, the motors can control the transformation of all panels according to the data of light intensity captured by the sensors. Inspired by the prototype, I found out that the panel materials need to be supported by profiles, and the profiles can vary in shape, division, and angle to create different visual effects. In the final system design, I need to figure out what is the proper scale and distribution of the units and what is the interior experience after the system is applied to a building. For the room scale, we can see that options with less vertical divisions and 2 to 4 horizontal divisions behave better. Also, vertical division can be weighted. It shows that uneven distribution can improve the outcome. In order not to block the views from the interior space, the material of the panels could be some kind of translucent membrane. This facade system can also be applied to different types of buildings. For example, I tested a high-rise building, the World Trade Center proposal, with uneven panels, and a multi-story building, the Tianjin Binhai Library, with even panels. The system works well with this kind of planar surfaces and conforms well with the building footprints and existing horizontal facade elements. Finally, I also created this virtual indoor space for users to interact with different input parameters such as profile type, division number, and evenness. Besides the improved light behavior, the interior experience can also be peaceful and amusing, with panels slightly moving in a day. Looking back to the criteria I set up for this system design, there's one part I didn't think of deeply. That is the human manipulation of the system. Originally, the users should be able to set the preference of the light behavior along with the automated process. Because of the coronavirus condition, I cannot develop the prototype with a better control process and algorithm. Therefore, the main focus of the thesis is about how to utilize the digital evaluation tool to find out a better geometry and achieve a sufficient and uniform light condition considering the reflection attribute of light. Thank you for your listening.